Now, there's another problem also. Starting this semester, they've not allowed any cross-linking of classes. What that means is I'm teaching a double section. In the past, I was able to link those two sections together so there'd be only one Canvas shell. Now I have to have two Canvas shells, one for each section. So that means I have to, whenever I update one, I've got to remember to update the other one. So, and I'm old, what can I say? Sometimes I forget. So anyway, so sometimes there'll be a disparity between the two Canvas shells because of that. No, one for the Friday lab people, one for the Saturday lab people. So if you go to modules and you go down to Unit 1 at the bottom, you'll see the videos. And you should see a date also by it when that occurred. So this was August 25th. We went over significant figures. So if you click on it, it goes to this page. And here's the link here. Oh. When it works. I don't know why this is not working. Let's see. This one works. I have to just redo the link. But anyway, then it goes into, there I am with a different colored shirt. Okay. So that's how to find them. Okay, so we're going to actually start talking about chemistry today, as opposed to doing word problems and mathy stuff. What I want to do is bring you through the development of the current atomic model. And the belief today in the last 180 years or so is that matter is composed of atoms. Atoms are the most identifiable unit of an element. Identifiable. Okay, so what that means is that if I have an atom of gold, it acts like gold. If I subdivide that atom, it no longer acts like gold. And the word atom actually comes from Greek atomos, meaning no cut. Now, let me show you what happened. So let's go back a while, about 1800 years ago. There were two people, Democritus and Aristotle, that were kind of political rivals. They were philosophers, and they were kind of theoretical scientists at the time. And this is what Aristotle believed in. He believed in there were four elements, and everything is made up of those four elements. Democritus didn't believe that. What he believed, if we took an apple, and had a couple knives and went. If I cut the apple in half, is it still an apple? Yeah. If I cut that apple again in half, is it still an apple? Yeah, I took my two knives out and went, kept cutting and cutting and cutting and cutting and cutting. Got down to the point where all of a sudden it's no longer an apple. That's what he meant by no cut. No cut in Greek is atomos, and that's where the word atom comes from. Now, Democritus's ideas about the atom were very unpopular. Everyone loved Aristotle. It's kind of like politics nowadays. Everyone loves a certain candidate versus the other one, you know, and they all loved Aristotle up until. Now, it also depends on what part of the world we're talking about. Because science was proceeding at its own pace in different parts of the world. There was Asia, there was the Middle East, there was Europe, and each of those had their own science going, independent of the other, because the communication in those days was so poor. So we can credit Democritus to be the first person to come up with the word atom and the concept of the atom. Concept of the atom. Up until like the 1700s, there was a concept called alchemy. Alchemy was kind of a pseudoscience trying to make reality out of what they knew at the time. The problem with alchemy is that very few people had the wherewithal to kind of do anything and have the resources to do anything. Normally they work for a king. And what did the king want? Gold. So one of the chief jobs of the alchemist was to convert cheap metals to gold and silver, like lead to gold, lead to silver. And now that's called transmutation. So if you study nuclear chemistry or nuclear physics, you'll talk about transmutation all the time. It happens in our atmosphere, happens in the sun. It's very common, but it requires great amounts of energy. But in those days, they didn't know any of that. They didn't know what was going on. There were two big problems with alchemy. Two major ones, anyway. If you're a scientist today and you come up with a big finding, you've got to make it so that someone else can replicate what you've done. In other words, it has to be repeatable. If it's not repeatable, it's not acknowledged by the scientific community. In fact, there was a big scandal in Japan about 15 years ago regarding the discovery of a new element. And they had to pull it back because it wasn't repeatable. So alchemists purposely kept their work secret because it was a source of power. So they really couldn't prove anything because they weren't able to replicate it by someone else. Another problem was, if this is a in this country, this is a set of horrendously poor goggles. If we go to Japan, these are not goggles, the English word, it's another word. If you go to Africa, it's another word. But it's still the same thing. Alchemists had a problem, particularly with chemicals. All the alchemists had different names for all the chemicals. So it was very hard to do anything reproducible because everyone used different names for everything. And there was one other real problem in those days, which was one of the reasons why there were kind of three elements, not elements, areas of the world where scientific research was going on, 1,000 or so years ago, is because of the lack of communication. Now, if you think about medieval Europe, we had these big cities, quote unquote. Paris was about the size of Rockland. Paris, back in those days. London, size of, not very big by today's standards. The problem is, how did you communicate from London to Paris? You either walked, you're on a stagecoach and a ship, in other words, really slowly. So there was a big lack of communication from one village to the next. Even if they did want to, distribute information and findings and stuff, it was very difficult because of the lack/poor communications. So those are which was kind of related to these two. During about a millennia or so ago, the Middle East was a hotbed of science. Big deal. Lots of new discoveries and stuff were there. In fact, this guy here, I cannot pronounce his name, is considered the grandfather of modern chemistry. All that happened in the Middle East. No one gives credit for these other cultures contributing to science, except for me. Same with Asian. They came up with all this stuff, 1,500, 2,000 years ago. Europe, Western Europe was running around in caves and then, dyeing techniques, pottery, gunpowder, noodles. So my point here is that there was a lot of stuff going on in the world, but because of poor communications, that information wasn't shared. Okay, so the first real physicist that came out, his name was Dalton. Dalton started to accept Democritus' idea of the atom. And these were some of the things that he said. Each element is composed of tiny indestructible particles called atoms. Of course, they're not indestructible, but in those days they were. The atoms are unique. They have a specific mass that's different than other elements. And they combine in simple whole number ratios. In other words, what's the formula for water? H2O, it's not H2.10. It's H2, the whole number 2. Next guy named Thomson, he said, well, here's the atom, but there's some charge associated with the atom. So he came up with the concept of the electron. And the other thing he came up with is how is it organized inside the atom? And his proposal is it's not organized. And he used the metaphor of the plum pudding, just kind of blobbed in there with little bits of plum floating around with no organization to it. He also noticed that these negatively charged electrons should have made the atom negative, but the atom was neutral, meaning that there had to be something to balance that negative charge. So he kind of invented the proton, the positive charge. He didn't have any experiments to prove it. He just said to justify the electrical charge of the electrons, We have to have something to balance that. So you can credit Thomson with two things: plum pudding model and discovery of electron. Now, getting into modern science, we have to replicate what Thomson did. So Rutherford, another scientist, decided to test his model. And this is how he tested it. He decided to bombard a very large atom of gold with a particle, and then test Thomson's theory of the plum pudding model. So what he did, he basically had a ray gun. He was shooting alpha particles, which is a very heavy particle with 2 protons and 2 neutrons. He shot that out of a little hole in a lead box at the gold. And what happened was 99% of the alpha particles went through the gold atom. Now, with plum pudding model, 100% should have been ricocheted off. So Rutherford had a conundrum here. He was going like, wow, this should have all backfired. So Thomson's model has not been proven. It's been disputed now by Rutherford. So Rutherford proposed that most of the inside of the atom is nothing, except for a tiny, very dense blob of matter right in the middle of the atom. It's called the nucleus. So Rutherford discovered the nucleus. Now, this was very controversial. A lot of people today don't understand that, even today, that most of the atom is nothing. We have some arbitrary electrons in there doing their thing. And electrons are very, very small compared to protons and neutrons in the nucleus. Now, let me give you a perspective on that. Let's take a giant football field and put a marble in the middle of that. So that's the size of the atom, and that's the size of the nucleus, the little marble in the middle. And think about that. We've got, what do like charges do? Do they repel or attract? They repel, right? Just like 2 north poles on a magnet, they repel. Yet they're smashed together in that little tiny area. So there's some extremely strong forces keeping those protons together. So when we do nuclear reactions, that's what's released, that energy that's holding those protons together. And it's a lot of energy. So Rutherford, nucleus. He also got a Nobel Prize for this. Now, to show you how small an electron is, bless you. Look at the ratio. We have 1.6 times 10 to the minus 27 grams versus 0.000091 times 10 to the minus 27 grams for an electron. So that ratio is like almost 20,000 to 1. Yet the charge on an electron is a full 1, -1. The charge on the proton is a +1. So that little bitty electron has a horrendous amount of charge to mass ratio. Now, as far as this class is concerned, we have 3 subatomic particles: protons, electrons, neutrons. But there are a whole bunch more charged particles running around inside there. But we're only going to consider those 3 for this class. In fact, when you get into 1A and 1B, you're only going to consider those three as well. But there are, and they all have funny names, really funny names. In fact, if you take a neutron apart, you will find two things in there. You'll find as far as this class is concerned, you'll find a proton and an electron together. Together, they make up the neutron. So electrons are in two places in the atom, outside the nucleus and inside the nucleus both. Okay, so protons and neutrons have similar masses. Electrons frequently they will say has no mass, but they do have mass. They have a very small mass, but they have mass. Okay, now this is something really important. What determines one element different from another is not the number of electrons, not the number of neutrons, it's the number of protons. If the protons change, like in a nuclear reaction, the element changes. That's called transmutation. That's what the kings were trying to get the alchemists to do a long time ago, is to basically change the number of protons inside that lead to be at the same number of protons as the gold. Okay, and that's abbreviated uppercase Z. So whenever we have an element, let's take carbon. The symbol for carbon is C, as you all know. Okay, there are two numbers associated with each element, a superscript and a subscript that's in front of the symbol. Okay, the subscript is the number of protons. This is the atomic mass. And it's equal to protons plus neutrons. So I said a couple minutes ago, I said the number of protons determines the elements. So we can have elements with different numbers of neutrons. And to designate that, we have to change the top number. So in this one here, how many protons do we have? 6. How many neutrons? 6, because 6 plus 6 is 12. What about over here? How many protons? And neutrons? 8. Because it's got to be equal to atomic mass. So to write these two out, so one way to write this is like this. So we have the element symbol. In this case, it's carbon, so it's C. The top number on the superscript side has to be the mass of the protons and neutrons. In this case, it's 6 and 6 is 12. The bottom one's the number of protons. That's one way to write that. And this is called carbon 12. Okay, the other one is called carbon-14. When we get into later in the semester, we're going to be using these numbers a lot. You look at the periodic table for carbon. Okay, there are two numbers for each element on the periodic table. One number is the number of protons. The other number is a decimal number. That decimal number so that's the average of all the isotopes. The C14s, the C12s, the C13s, the C11s, all those isotopes together come up to be 12.01. You average it out. Now, an average, as all of you know, take the number, take the mass, take the number, and divide the mass by the number. So what's the most common isotope for carbon? Who said 12? Yes, because the average is closest to 12. That means there are more 12s than there are 13s and 14s and 11s and 10s. So you can tell what the most common isotope is by looking at the average down there, the decimal number. That's called the atomic mass. So in the case of beryllium, it has 4 protons. So the Z for beryllium is 4. The chemical symbol is Be. Now, I'm going to be extremely picky about your symbols. When you write down a symbol that's 2 letters long, the first letter has to be, no exceptions, uppercase. The second letter has to be lowercase, no exceptions. Now, let me show you why that's important. CO and CO. Big C, big O. Carbon and oxygen together in a molecule. I know that because the O is uppercase. Below, that is not carbon monoxide. That is cobalt because it's uppercase C, lowercase O. And we have combinations like this that exist fairly often. So it's really important to distinguish when you're writing things like barium, Ba, big B, little a, gold, Au, big A, little u, silver, Ag, big A, little g. Okay, I can't stress this more. Now, if you're used to writing all your letters in uppercase, just smaller, I had a Coast Guard guy in one of my classes, I don't know, about 10 years ago or so. And by international law, everything he wrote, I should say, had to be uppercase. And he'd been doing that for, a number of years. So he was really used to writing everything in uppercase. And he comes to my class and he's like, He says, "You're killing me. What am I supposed?" I said, "You just have to do it. I'm sorry." And I gave him this CO example. And he goes, "Man." So he was a really smart guy too, but he had a real problem. He had the most interesting job. He inspected container ships, and he had the wildest stories about what goes on in container ships. He always had to have a hazmat suit on. Those things are indestructible, except for one chemical. Who's watched Breaking Bad? Anyone? Okay. Why did the tub fall through the floor? That's right. And what was the chemical that ate through the floor? It was hydrofluoric acid. That's right. HF. HF will go through a hazmat suit. So he was working, now going back to the Coast Guard guy, he was working one day and he noticed a hole in his hazmat suit. He took off his hazmat suit and there was a hole in his arm because it dissolves flesh. That's why they wanted to use hydrofluoric. They wanted to dissolve the body. And so he ended up showing me the scars, a big round scar about that big. And he lost a fair amount of nerve damage. And so anyway, he had a whole bunch of stories like that. He almost drowned because he was at a plant that made antifreeze, and one of the big giant tanks broke and came careening down towards him. Lots of stories like that. Okay, so getting back to this. So if it's a 2-character symbol, make sure the second character is lowercase and the first character is uppercase. Now, if you were an organized guy or gal, and you had a whole bunch of elements in front of you, and each one had different properties, you would have a tendency to want to organize those elements into something. There were 2 people, 2 physicists a while back. One was a Russian, and the other one was, I forgot what the nationality of the other one. One was a geologist, one was a physicist. The geologist discovered this first. The geologist discovered the periodic table first, but he kept it to himself and his buddies in the geology world and didn't publish. Mendeleev discovered it also, but published. So all the credit goes to Mendeleev, not the geologist. This is what his first periodic table looked like, his scribblings. You know, you compare it to our modern periodic table, huge difference. So basically, this is how it works. He took all the elements at the time that he had was available to him, and he put them in a line. And he noticed that every now and then, the chemical properties would repeat. It would be, you know, whether they're water soluble, whether they're magnetic, whether they were formed in ion easily, conduct electricity, whatever. The properties repeated. So what he did is he cut that line every time they repeated. And then he brought that section underneath the previous section. So we went from 1-dimensional to 2-dimensional. So that all the elements at the time that had similar chemical properties were lined up in a column. And that's what they mean by grouping elements by similarity of chemical properties. Because their chemical properties were very, very similar, almost identical. Now, you're going to have to know you're gonna have to know some things about the periodic table. I already talked about the two numbers in each box. One is number of protons, the other is, by the way, some of you are taking pictures of this. I have these available already. I'll show you how to find them. And they'll be much clearer in your pictures. All right, and also the atomic mass, which is the average of all the isotopes. Now, these are the columns that I was referring to. They're all numbered. And we're not going to all of the columns have numbers, and they differ from these inner ones. The numbers we're talking about are the A numbers. So it goes 1A, 2A, 3A, all the way up to 8A. All the way over to 8A. And you're gonna have to know 4 of them. 4 of the most common ones. Okay, so 1A is called the alkali metals. Second one next to it is called the alkali earth metals. Eight A are noble gases. And 7A are the halogens. Now, we're going to divide periodic table up into 2 parts. We're going to have the left and the right in the middle. The middle are the bad boys. They do things differently, and they're very inconsistent. The left and the right are very, very consistent in terms of their chemical properties. Okay, so the alkali metals always form a +1 ion charge. The alkali earth metals +2. Then we're going to jump across the transition metals over to the other well-behaved side, and these form +3. And what do you think the next one's going to form? +4. Now there's an issue with that. Okay, going to the far right, the halogens always form a -1 ion. Going to the left, -2, -3, and what comes next? -4. So there's a problem here with the carbon group or the carbon family, is that they want to form a +4 or a -4 charge. So what the carbon family does is they don't do either. They don't form an ion. So these columns are called groups. The rows are called periods. So the important thing now to distinguish between groups and periods. Groups have similar chemistry. Periods don't. They're just on the same row going across. Okay, so let's look inside the nucleus. Let's look at phosphorus. Okay, how many? Well, it's hard to see up there. Okay, how many protons does phosphorus have? 15. Okay. So there are 15 P's in there. I don't want to draw all the 15, but there are 15 P's in there, 15 protons, and a scattering of neutrons as well. Okay, not all protons are created equal. When we look at a neutral atom, there are as many electrons as protons because that's what declares neutral. So how many electrons does phosphorus have? 15, because it has 15 protons, 15 electrons. Each one cancels out each other, so the net charge is 0. Now, the problem with electrons is they're organized in a certain way. Now, the last time we spoke about the history of the development of the atom, we left off at Rutherford. Rutherford discovered the nucleus. He didn't talk about the organization of the electrons. Along came a guy on the turn of the last century named Bohr, who said, that's poppycock. The electrons are organized. And he used the metaphor of our universe to describe the organizational setup for the electrons. His idea is, supported with a whole bunch of math, is that the electrons are circling the nucleus, similar to the way the planets circle our sun. Same idea. And there's some shortfalls in that can't be explained, and that's why we moved on to another model. But basically, Bohr said that the electrons are set up and that each orbital can only hold a certain number of electrons. And so on. So the excuse me, the innermost electron orbital can hold 2 electrons only. Then we go out to the next orbital. It holds 8. And the next one holds 18. And it keeps building. Now the electrons are required to stay on the orbital. They They can't go off the orbital. And the space between the orbitals is nothing. So the only place electrons can be or allowed are those orbitals. Now, later on, we found out the orbitals can be subdivided into suborbitals and all this other stuff. Okay. Okay, so the electrons are divided into two main groups. Core electrons and valence electrons. Okay, the valence electrons are the electrons in the outermost orbital. The core electrons are in from that. That's either one or many. Now, the important point of distinguishing between core and valence electrons is all the chemistry is done with valence. So the core electrons, because they're so stable, I mean, they are super stable, that there's no chemistry done with them. So the only electrons we need to consider are the valence electrons, because that's where the chemistry happens. And those are the outermost orbitals. So how do you figure out this valence electrons? You go to the periodic table. That's the valence electrons is the lowest row. So here we have phosphorus. So the valence electrons for phosphorus lie on the third orbital out. That's the most outermost electrons for that phosphorus. That means those are valence electrons. And those are core. So if I ask you how many valence electrons does phosphorus have, you have to be able to count. So valence electrons for phosphorus is, now there's a trick that I'm going to get to later in the semester, is these middle transition metals are moved down one. So really the valence kind of goes like this for phosphorus. So because when we try to go, we have that big blank area there. Well, not blank really, it's just down below. Okay, so we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But when we talk about the chemistry of phosphorus, the transition valence electrons don't come into play. So really, all we're talking about is 1, 2, 3, 4, 5. So for phosphorus, we have 5. How many core electrons does phosphorus have? Total number of electrons is what? 15. 5 of those are valence. The rest are core. 15 minus 5, right. But the valence electrons is where all the action is. And the electrons around that phosphorus valence group are very unique, and that allows it to have unique chemistry. Now, what I'm going to have you do is okay, we're going to, as a class, go through this here. And what I've done is I've left off some numbers, and you're to fill in the numbers. So let me do the first one for you. And it would be helpful if you had a periodic table. There's one up there. And in your lab packet, you have a nice periodic table. So what is the name of the element B? Boron. And which boron is it? Oh, I can't write on this. Why can't I write on that? I'm going to back out of this and get into a screen where I can write on it. Okay, sorry about that. All right, so okay, so B is boron. Now, what I'm going to have you do is you're going to be putting what isotope that boron is. Boron 11. And that comes from here. What's the atomic number for boron? 5. How many protons does boron have? 5. Oops. So atomic number and protons always are the same, no exceptions, always the same. Now, how do you know how many neutrons boron 11 has? Well, it has 5 protons and the atomic mass is 11. So how many neutrons does it have? Well, if it has 11, that means 5 from 11 is 6. That's where 6 comes in. So the atomic mass is going to be 11. Now these are neutral. The top of the worksheet, I have neutral atoms. That means there's no charge. Right now we have a charge of +5 with the protons. So we have to balance the +5 protons with how many electrons to be neutral? 5. So the protons and electrons, if it's neutral, are equal. So I filled in all the boxes for boron. Let me do one more. What element is atomic number 11, or Z equals 11? Sodium. Okay, and what's the atomic mass for sodium? (24), right? So that isotope is sodium 24. And we always know that the atomic number and the number of protons are always equal. So how many neutrons does sodium 24 have? How many neutrons? Now remember, protons plus neutrons equals 24. Right, 13. How many electrons? 11. Okay, so go ahead and work these guys just to kind of get used to doing numbers of, and you'll have a subset of this on your test, by the way, to fill out. Now, the next one we're going to do is one with ions. I haven't talked about what an ion is or anything like that. So this is for a neutral atom. So go ahead and start working on these. This way I'll get you really into your periodic table, all that good stuff. Now you can see okay over here? Yeah, I guess you can see it. That's a handy place to put. Now, if you want a PDF of this, you can go to Canvas and then download it from files, worksheets, one.
Sodium one says 20, no, it says 24. And this one says 22.99. Is that?
Remember, this is the average of all the isotopes.
Mhm.
So class, do not use the decimal number on the periodic table. Purpose of the decimal number is to show you what the average of all the isotopes. We're working with one isotope.
So just this.
Yes.
I just want to make sure.
So all these are integers. Yeah. You have your lab packet yet? That's where it is. Hmm?
Where do I get the lab packet?
Bookstore. So it's the one we're doing now. Oops. The one we're doing now is this one here. I don't know. So we know what time the bookstore closes? Probably. Is it like 4 or 5? I've never come in this way. I was coming from there.
They give you keys to unlock the doors.
Oh, yeah, because no one's gonna, no, I mean, no class tomorrow, but normally on Saturdays, if they don't have an activity, the whole building's locked, so I have to unlock everything.
Okay.
So, you wouldn't know, you wouldn't know what isomer. The number of neutrons is the key. And the neutrons can change from one isotope to the other. That's right. If you didn't have 24, it's just a nice. These are just random isotopes.
Here, then it's 11, but they don't say anything about the 6. And we know that the number of protons is 7. We don't have any number of neutrons. We can't find it.
But you know the average atomic mass, that's the decimal number of all the isotopes in nature.
Can't see them because I forgot my glasses today, so I'm looking at it online.
Oh. We talking about the sodium one?
I can't really see the whole thing. I'm.
Okay,
together, I
so
looked it up
it's
on-
20, yeah, it's 22.99. So 23 is the most common isotope for sodium, but not all the isotopes. So this specific one is 24. But I have to give you enough information. Yeah. I have a student with an accommodation that has to use this door.
Yes, that's why the door was open.
Yeah, right.
Yeah. You're gonna wanna contact community safety. They unlock all doors.
I have a key.
Oh, okay, then you're good.
I just never come this way.
Oh, okay, yeah, this
So I
is,
have to find,
yeah, yeah. I know you're on your lunch break, so you can go, but all I was gonna say is like, when I reported, I was like, hey, I don't want there to be another time.
okay, why don't you finish these up at home on the next time we meet next Friday. I want to look at the situation where if we have an ion, and we need to look at electrons, protons, neutrons, isotopes. Yeah, it's going to be gallium dash
Yeah. I-
68. Yeah.
Sorry, yeah, thank you.
Yeah.